Welcome back. So I want to talk today about a couple of additional types of functions. I said we were going to start motivating where limits come from, but I actually sort of lied in the last video because there's a few more types of functions that I do want to remind you about before we get into that kind of thing. So let's start with that. And the types of functions that I want to remind you of are the exponential functions and the logarithmic functions. So let's start with the exponential functions. The exponential functions, these are any function that has the following form. F of x is equal to a to the x, and some people will also allow you to put a constant out front like this. Put a constant here. You might potentially put constants up in the exponent as well. Little slight different complications that we can come up with, but the most basic format is just some number raised to the x. And the conditions that we generally speaking want to have here are that a is a real number that is bigger than 0 and a is not equal to 1. The reasons we put those conditions on there is because if a were equal to 1, this would be very boring. This would be just a constant. And if a is negative, then we have to interpret what's going on here in terms of complex numbers rather than real numbers. So if we want to keep everything in the real number system, then we want to put these restrictions on there. Well, we want to put this restriction on there. This restriction just comes from wanting this function not to be a simple constant function. And in this expression, this number here is called the base of the exponential function. Now, how do you define something like this? Well, it turns out that defining exponents is actually a bit of a tricky thing, and I think that we should go through carefully how you do it, because it's kind of a good introduction to the way that mathematicians reason as we try to build up our mathematical tool set. This is kind of the way that people would have thought about this when they first started. Okay, so the most basic type of exponent is when the exponent itself is going to be a natural number, like 1, 2, 3, 4, 5. So how would we define a to the n when n is a natural number? Well, the answer is we define this to be repeated multiplication. Multiplication is actually repeated addition. If you remember, you define multiplication in terms of repeated addition. Well, you define the exponent in terms of repeated multiplication. Okay, so a to the n would be a multiplied by itself n times. So we've got n copies of a here multiplied. And that's great, but it only defines the exponent operation if the exponent happens to be a natural number. So what do we do if it's not just a natural number? What if it's something else? Well, the answer is, in one sense, it's sort of like we could define it in a bunch of different ways, but we want to define it in a way that is useful and that sort of preserves what's nice about this operation for natural numbers. So I want to show you two properties of the exponents with natural numbers that are really kind of cool and that we would like to preserve as we generalize exponents to non-natural numbers. So throughout this, we are going to treat m and n as natural numbers, for the moment at least. Later on, we're going to generalize this, of course, but for the moment, let's consider these to be two natural numbers. Then there's two properties that we're going to notice here. First of all, a raised to the m times a raised to the n is equal to a to the m plus n. In other words, when I multiply two exponential expressions here, I get another exponential expression, and the new exponent is the sum of the old exponents. You're probably familiar with this from your pre-calculus classes, or maybe you didn't call it pre-calculus, but presumably, hopefully, you guys have seen these kinds of things before. And then there is a second, maybe we should talk about why is this true? Well, the reason this is true is because this is going to be m copies of A times n copies of A, while in total, that is m plus n copies of A here. And that gets us to a to the m plus n by the definition. So when you write these out, it's actually not too hard, I hope, to see why this rule is true when the exponents are natural numbers. Okay, so that's great. For natural number exponents, we have this property. Now, there is a second property that we can do here, and you might want to actually take a minute to try to convince yourself why this property is true before I explain it to you. So the next property is that if I have a raised to the m and then I raise it to the n afterwards, well, this is actually equal to a to the m times n. In other words, I multiply nested exponents. Now, take a moment and see if you can use a similar kind of reasoning to what we just did to convince yourself that this property has to be true. Okay, so were you able to see something? The idea is pretty similar to what we did before. If I take something and raise it to the n, this is actually a to the m times a to the m. There's n copies of this. N copies of this a to the m. But each one of these is actually little m copies of a. In other words, this is actually equal to, here's m copies, here's another m copies. Let me erase this for a moment just so that everything isn't quite so cluttered. Here's another m copies. And how many of these things do we have? Well, in total, we've got n of these collections. But how many a's do we have? N times n, because we have sets of m, and we've got n of those sets. You multiply those to get the total, and this is going to be m times n copies of a. And that gets us to this property here. So these two properties are actually something that is really, really cool here, because multiplication is getting turned into addition in some way. And here, exponentiation is getting turned into multiplication. Somehow we're able to take a more complicated operation and turn it into a simpler operation. The fact that we can do that is really, really, really useful. And it's something that we want to preserve whenever we talk about exponentials. So we're going to want these two properties here to continue to hold true for other values of exponents when we start generalizing these things, okay? And it turns out that if I want to make sure that these two properties continue to hold, there is only one way to generalize the exponential operation so that I can use more general exponents. There's only one way to do it and keep these things going, keep these two properties going in a way that is sensible. So we'll talk about how that happens as we move along here. So first of all, I want to generalize this to the whole numbers. How can I generalize the exponent operation to the whole numbers? Well, the main thing I got to do, because I already know how to do it for all the natural numbers, the main thing I have to do is I need to generalize it to the number 0. I need to be able to define what is a to the 0. Now, most of you probably already know what a to the 0 is. Okay, that's a terrible looking 0. That's a slightly better looking 0. Most of you probably know what a to the 0 is, but I'm going to tell you why we define it the way that we do. Well, the answer is we want to have the following property. We want to be able to say that a to the 0 times a to the n should be equal to a to the 0 plus n, but that is just a to the n. If I divide both sides here by a to the n, I get that a to the 0 had better be equal to 1. That's the only way that this property can continue to hold. So we're going to define any number to the 0 to be 1. That was actually fairly straightforward. And it turns out that getting this to the integers is kind of equally straightforward. So let's see how we can go about generalizing this to the integers. The only thing I need to know is what is a to the minus n going to have to be, where n is, again, a natural number. Remember, for the moment, I'm thinking of m and n as natural numbers whenever I use them, okay? So keep that in mind. I'm not writing it out repeatedly, but it is still a natural number. So how can I define this in a way that makes sense? Well, we want a to the minus n times a to the n to be equal to a to the minus n plus n, which is equal to a to the 0, but we just said that that has to be equal to 1. Well, what does that mean? The only way that this is going to be true, I can solve for a to the minus n by dividing both sides by a to the n. A to the minus n is 1 over a to the n. It is the multiplicative inverse of a to the n. And so that's what we're going to define it as. We are going to define a to the minus n to be 1 over a to the n. It's the only thing I can do that preserves this idea that when I have a multiplication like this, I just have to add the exponents. Now, you do want to take a moment and carefully verify that these definitions really do work, that they don't create some kind of a contradiction elsewhere. But it turns out that it's not too difficult to verify that all the properties of exponents continue to hold for the integers if we define things this way. And notice, to get this for the integers, the only property I needed was that I want to preserve the idea that multiplication becomes addition. So we now know that multiplication becomes addition for any integers. So that's excellent. We have that. And in fact, the second property holds true as well for the integers. Now, again, I will leave it to you guys to check and make sure that our second condition, the one about nested exponents, continues to hold true. So now we have another problem. Let's suppose here that P and Q are integers, and we want to know what is A raised to the P over Q. In other words, we want to try to define what is a rational exponent. Well, you probably already know the answer, but once again, I want to show you why we want it to be what it is, why we need that to be the case. So this time, we're actually going to use the second property, the nested exponent property. And I'm going to start with a to the 1 over q. I want a to the 1 over q raised to the q. This should be equal to a to the 1 over q times q, which is just a. Well, the only way for that to be true is if a to the 1 over q is the qth root of a. And we're going to assume here that q is bigger than 0, which we can do because for any rational number, the denominator of the rational number cannot be 0, and we can always take the denominator to be positive. So strictly speaking, this condition really doesn't limit us at all when I say that. We can kind of make this decision and it doesn't affect anything that we do. So once I have this, well, now I can say I also want a to the p over q to be equal to a to the 1 over q raised to the p. But that, from what we just saw, is the qth root of a raised to the pth power. And we know how to do this for any given integer exponent. So p can be any integer, positive or negative or 0. And this definition works just fine. So we have now defined exponentiation for all of the rational numbers. What about the real numbers that aren't rational? What about the irrational numbers? Well, here's the nice thing about doing it for the irrational numbers. To make these ideas precise is actually a big part of calculus. But so now what we have is we now know a to the x when x is a rational. But what about if it is an irrational number and we want to define it? So what about a to the x for x an irrational? Well, it turns out that there's an actually kind of obvious way to define this. Now, I want to emphasize we cannot do what we just did to generalize it further. We cannot just say, okay, let's try to keep these properties. The problem that we have here is that irrationals cannot just be expressed from rationals using simple arithmetic operations. Like a rational number is a ratio of integers. I can write it as one integer divided by another integer. Okay, that's great. But the problem here is that that does not allow me to write an irrational number. So we are going to need to be a little bit more careful here about what we are doing. And what are we going to put in here? Well, the way that we're going to do this is notice for x rational, a to the x is always increasing or always decreasing. And in particular, it is increasing when a is bigger than 1, and it is decreasing if 0 is less than a is less than positive 1. Okay, so we have this nice property here where it's always increasing or it is always decreasing. So what does that mean? Well, what it means is this. If x is an irrational number, then x splits the rationals into a set A, which is going to be the set of all numbers p over q such that p over q is less than x, and into the set B such that, which is going to be p over q such that p over q is bigger than x. And together, A and B are going to give me all rational numbers. Now, the thing is that if little a is in, or why do I want to use little a? Let's not use little a. Let's say if, what letters do I want to use? Let's use R. If R is in A and T, or let's use S because it's RS, yeah. Let's use S is in B. And let's just do the case where A is bigger than 1 here. If it's less than 1, it's the same kind of idea, but all of the inequalities get flipped around. Then A to the R is always going to be strictly less than A to the S. Because in this case, R is smaller than S. So since this exponential function is always increasing, that means A to the R has to be smaller than A to the S. And what we are going to do is we define A to the X to be the unique number bigger than all of the a to the r's and smaller than all a to the s's. In other words, when you look at the exponential applied to these rational numbers, what you're going to get in terms of your graph is going to be something that looks like this. So let's suppose that this is our little number x. If I look at the rational numbers, the picture that I'm going to get here for my exponential function is going to look like this. Well, let me make it a little bit more shallow so that we can have everything on the screen here. So you know that the exponential function looks like this. I'm dotting it because we're only evaluating it on the rational numbers. And you'll notice that basically what happens is there's going to be this split here where as long as my r value is smaller than x and my s value is bigger than x, a to the r will always be down below this horizontal line and a to the s will always be above it. And so what I want to do is I want to say a to the x is going to be specifically that one point, that height of the horizontal line. The reason I want to do that is because if I do that, then it preserves the fact that the exponential function for all real numbers is going to always be increasing when a is bigger than 1. If I did anything else, then this function would start jumping around in crazy kinds of ways. And so what we want to do is we want to define this function, this exponential function, in such a way that it preserves this nice always increasing property. Of course, if a is smaller than 1, then you have to take this picture and mirror image it. And so then everything comes down, the roles of r and s get switched. But it's the same basic geometric argument where once again, we see that there's this horizontal line that splits everything that is to the left versus everything to the right. The image of everything to the left is on one side of the horizontal line. The image of everything to the right of x is on the other side of the horizontal line. And therefore, we want to define a to the x to be exactly on that horizontal line. This is actually kind of the very first thing that we see that is really a part of calculus proper. In fact, this idea is the foundation or one of the founding principles of a branch of mathematics called analysis. And essentially what we're trying to do is to ask things like, if we know how to define a function for the rational numbers, is there a sensible way to make it work for the irrational numbers too? Well, the answer is yes. As long as it is a well-behaved function for the rational numbers, we can kind of go on and ask that it be a well-behaved function for the irrationals as well. And in this case, what we mean by well-behaved is always increasing or always decreasing. It turns out that you can actually do it even if it's not always increasing or always decreasing. It turns out that as long as it's sort of on any given small enough interval is either increasing or decreasing, then you can still do this trick where you kind of fill in the holes at the irrational numbers. Because what you do is you say, okay, on this interval, it's increasing, so we fill in the gaps by finding the horizontal lines and keeping it increasing on this interval. If it's decreasing, then we want to keep it decreasing for the irrationals as well, so once again, we fill in the gaps. So even if we had a more complicated function that maybe isn't always increasing, isn't always decreasing, we can still do this kind of filling in the gap stuff. Okay, so those are the exponential functions. And the basic shape of the exponential functions, just to remind you, there's kind of two possibilities for what they look like. And give me a second here because I'm pretty slow at drawing stuff. So one possibility is that they look like this. This is for a bigger than 1. And they will always go through the point minus 1, comma 1 over a. They'll go through the point 1, comma 0, and they will go through the point 1, comma a. Okay, those 3 points are very important points to keep in mind when we're talking about exponentials. And those 3 points show up again if we're talking about a less than 1. It's just that everything happens in the opposite direction here. So this time, minus 1, comma 1 over a is actually bigger than 1, and 1, comma a is smaller than 1, so we get the same shape, but it goes in the opposite direction here. The domain of a to the x is always going to be all real numbers, and the range of a to the x is always going to be all positive real numbers. At least as long as a is not equal to 1 and a is bigger than 0. Now, once again, if we start messing around with negative bases, then all bets are off. And honestly, we're not going to mess around with that in this class, because if you have negative bases, you can do it, but you have to delve really deeply into complex number stuff, and it's kind of more complicated. So for a start, we want to understand these functions when we're dealing with these conditions on the base, and then later on we hope that we can kind of move on to talking about other sorts of stuff. So that's a really brief review of exponential functions. Now, along with exponential functions, we've got another type of function that sort of goes with them, and these are the logarithmic functions. So the important things about logarithmic functions is that they're the inverse functions to the exponentials. So let me remind you what inverse functions are. We talked about the function composition in the previous lecture. And the thing about function composition is that if f of x is what we call 1 to 1, which means that if f of a equals f of b, a is actually equal to b. In other words, if my function takes each thing in its domain to a unique element of the range, then we call it 1 to 1. In this case, we can define f inverse of x so that f inverse of x being equal to y means that f of y is equal to x. So the idea here is that f inverse just takes whatever you did with f and it sends it backwards. It takes the thing from the range and it pops it back to where it came from. So you kind of have this idea that like f goes like this and f inverse just goes right back the other direction. If you think about these functions as sets of ordered pairs, f inverse just takes each ordered pair and swaps the order. It's actually a really cool thing here. And in fact, the way that you do this, the way that you switch everything around, allows us to see exactly what the graph of an inverse function looks like. So if f is given by the set of pairs x comma y such that y is equal to f of x, then f inverse is the set y comma x such that y is equal to f of x. And this makes sense as a function provided that the f here is 1 to 1. This will then still be a function. And the nice thing about this is that this means that if you take the graph of some function, so let's say this is my y equals f of x, here's my x and y. Well, to get the graph of the inverse, you just take the mirror image along the y equals x line. So everything gets flipped. Why does everything get flipped like this? Well, because to get the inverse, you're literally just interchanging the x and the y on your graph. You flop them back and forth, and when you do that flipping, the x-axis gets flipped to the y-axis, and the y-axis gets flipped to the x-axis. Now, it's really kind of hard for me to demonstrate, but take a minute here and convince yourself that, yeah, if I do that, that is the same thing as just grabbing the whole plane and flipping it across this diagonal line. Now, the important properties of inverse functions are going to be that f composed with f inverse of x is equal to x, and f inverse of f of x is equal to x as well. Notice also that when we do the inverse, it switches the domain and the range. So if I know the domain of f, that is going to be the range of f inverse. If I know the range of f, that's going to be the domain of f inverse. Now, how does this all apply to the logarithm functions? Well, the logarithm functions are the inverses for the exponentials. So log base a of x being equal to y, this means that a to the y is equal to x. Another way of thinking about this is that the log base a of a to the x is equal to x, and a to the log base a of x is equal to x as well. So these three different ways of writing stuff out, any one of these three is equivalent to the other two, and they define the logarithm functions. What does the logarithm graph look like then? Well, it looks like the exponential graph, except it's been flipped across that diagonal line. And so what we get is it will always go through the point 1, 0. You know, I think before I wrote 1, 0 on the vertical lines, and I meant to write 0, 1. So I apologize about that. When I was doing the exponentials, this point up here should definitely be 0, 1, not 1, 0. I have no idea why I swapped those in my head, but somehow I did when I was writing it down. Sorry. And then we have got that it's going to go through the point 1 over a, comma, minus 1 down here. Actually, why am I writing that up here? Let's put it down here. 1 over a, comma, minus 1. And then it is going to go through the point a, comma, 1. And we get this sort of picture. This is when a is bigger than 1. If a is less than 1, then you get the same thing, except it is flipped over the x-axis. So I'm going to leave that to you guys to figure out or to look in your book to see what that looks like. But it's the same shape, just flipped over. Now, notice that the domain for log a of x is going to be all positive numbers, and the range is going to be all real numbers. And that's true whether a is bigger than 1 or between 0 and 1. There are a couple of really important properties to the logarithm that I want to remind you of here as well. And those properties are that log base a of m times n is equal to log base a of m plus log base a of n. And why is that true? Well, this follows from the properties of the exponential function, because you see a raised to the log base a of m times n, this should be equal to, whoops, why did I write two equal signs? There we go. This should be equal to m times n. But this is a to the log base a of m times a to the log base a of n. And by the rules for exponents, this is a to the log base a of m plus log base a of n. Since the exponential function is 1 to 1, this exponent and this exponent have to be equal to each other. And there we go. We have now proved this property of logarithms. There is a second property of logarithms that's really important to keep in mind, and that is that the log base a of m raised to the n is n times the log base a of m. And once again, the way that we prove this is really kind of just to use the properties of exponentials. So a to the log base a of m raised to the nth power, this is equal to m raised to the nth power. However, this is also a to the log base a of m raised to the nth power, which, by the rules for nested exponents, is a to the n log base a m. Once again, because exponentials are one-to-one, that tells me these two exponents have got to be equal to each other. Now, what's cool about this is that it means logarithms take multiplication and turn it into addition of logs. It also means that they take exponentiation and turn it into multiplication. This has got multiple cool applications, although one of the applications is not as necessary anymore now that we've got computers. So one of the applications of this that people used to use, up until very recently in fact, was if you needed to multiply two very large numbers. That's kind of difficult to do by hand, especially if you need to do it very quickly. Well, what people did in order to approximate the answer, and back before they had calculators and computers that were easily accessible, what they had instead were these tables of logarithms. So what you would do is you would take the two numbers you wanted to multiply, you would look up what is the logarithm of the first one and the logarithm of the second one, you'd add those two, and then you would see what number had a logarithm close to that value, and that would very quickly allow you to look up approximately what m times n is. Now, it might be kind of like not exactly precise to use these logarithm tables this way, but if you're not trying to get an exact answer, if you're just trying to get an approximate answer, then that's good enough. So people would use these kinds of things when they were trying to do very quick mathematics. Like, let's say that you're, flying a plane back before they had good computers and stuff, and you're trying to navigate. Well, you might need to multiply some very big numbers very quickly, and you don't want to take 5 minutes to run through the whole multiplication procedure. Instead, you use this logarithm technique, and 20 seconds later, you've got the approximate answer. It's almost as good as using a calculator. And in fact, you can make a sort of a geometric calculator out of these kinds of things with what are called slide rules. So slide rules put numbers onto basically a collection of sticks. It looks like a collection of rulers that slide together, hence the name slide rule, because they're rulers that slide. But instead of having them equally spaced, they are spaced out logarithmically. And so what you do is, if you want to multiply numbers with a slide rule, you line up the numbers, you add the logarithms together, and the result tells you the product of those numbers. That's a really kind of terrible explanation in terms of you guys understanding what I'm actually talking about. What I said was correct, but if you want to know the details of it, you'll want to maybe look up slide rules. It's a kind of a cool application here. And again, back before we had electronic calculators, that was really, really useful. So now I personally am too young to have ever used a slide rule myself, but like a couple of decades before I was in school, slide rules are what people used. Now, the other application of this is one that continues to be relevant to today. So we're going to see throughout this course, when we do calculus, calculus can handle things that are added really, really easily. You can add all the stuff you want. Calculus doesn't care. It doesn't make things more complicated. When you start multiplying things, it makes things more complicated, by far. We can still handle it, but it definitely makes things more complicated. So one of the things that we are eventually going to see is that when we want to use calculus on certain functions, it can actually be easier to say, let's not work with the function directly. Let's work with a logarithm of the function, because we can split that logarithm into a sum. And once we've split that thing into a sum, calculus is now like, well, now we just need to deal with each of these things. The sum doesn't really matter. It doesn't make things more complicated. So as long as we can deal with calculus on logarithms, it's going to allow us to take what could be really tricky problems and turn them into fairly simple problems. And it will also allow us to take certain problems involving exponents that would otherwise be completely impossible for us to do and turn them into doable problems. Because as I say, we can use calculus with products. It's just more complicated. So in some cases, though, see, calculus doesn't work very well on exponentials directly. When one function is raised to another function, things get kind of messy. But if we can work with the logarithms instead, that is going to allow me to turn my question into a question about products, and it's going to become possible. It also turns out, and this is kind of going back to the way that we defined the exponential functions, because remember, we defined the exponentials, but potentially maybe there are other ways of defining exponentials. Maybe there's a different way of extending the notion of exponents from the natural numbers to the real numbers that would make more sense. Turns out the answer is no. It turns out that the way that we did it, the way that we went from the natural numbers to the real numbers, creates functions that have got these really, really cool properties in calculus. And because they've got these cool properties in calculus, they turn out to show up all over the place in the real world. Because it turns out, and we're getting a little bit ahead of ourselves here, but I want to kind of explain this to you so that you see where we're going with this and why this is so important and so cool. It turns out that the rate at which an exponential function is changing is proportional to the value of the function. Well, there's a lot of stuff in the real world whose rate of change is proportional to its value. Everything from financial mathematics, where interest is proportional to your investment, to biology, where the rate of change of a population is proportional to the population size, or even, like, let's say that we're talking about in medicine, you gave somebody an injection. How much of the stuff that you injected is left in their bloodstream? Well, it turns out the body processes things out of the bloodstream at a rate proportional to the concentration in the bloodstream. So it turns out that that gets described by an exponential function as well. It turns out that these things have applications in physics, a ton of applications in physics. Nuclear decay follows exponential stuff. Friction, moving under friction, follows exponential stuff. Even in psychology, this stuff shows up in psychology as well, and sociology. It turns out that it shows up in everything from studying how people forget to studying how rumors spread through a population. It even describes how diseases spread through a population. So it turns out that these functions that we defined because we wanted to have certain nice properties, like we said, okay, yeah, it's repeated multiplication for natural numbers, but we want to preserve those properties as we move to the real numbers. It turns out that those functions actually have these cool mathematical properties that result in them showing up pretty much everywhere. And because the exponentials show up everywhere, the logarithms show up everywhere as well, because logarithms are the inverses to that, and so they are also kind of ubiquitous. Okay, so what we're going to start in on next week is we are going to start in on sort of the motivation for why we actually need calculus if we're going to study this stuff. We already saw a little bit of that today, okay? Because when I extended the exponential definition from the rationals to the real numbers, we had to do this kind of reasoning where we kind of thought about, well, there's sort of this gap at every irrational number, but maybe we can just fill in that gap and define the function to be whatever fills in that gap. Remember how we had kind of all the rationals to the left map below this horizontal line, all the rationals to the right map above it. Well, let's just kind of split the difference there, and that's going to be the exponential at this irrational number. A big part of the foundation of calculus is to make precise this idea of there's a gap here that we can fill in. Because it's sort of intuitive in some cases, but in other cases, it's not maybe quite so easy to see exactly what's going on. And so our job next week is going to be to look at some situations where there's sort of natural gaps in a function and talk about the behavior of the function near those gaps and ask, under what circumstances can I just fill in this gap? Okay, so in the meantime, please do let me know if you have any questions, and I'm going to try to get the homework up as soon as possible and get everybody access to the homework and everything like that. This is my first time working with Cengage as well, so I do apologize if there's any kind of delays or anything, but I will make sure that nobody misses deadlines or anything because of a lack of access. We will get everything worked out, and I will give you guys extra time if you need it to make sure everything is actually working. So don't worry too much about that, but do try to buy the access code for the textbook and everything and the online homework so that we can try to get everything straightened out this week, or at least at the beginning of next week, and that way we'll be all set for the whole semester. Okay, have a good weekend, and I will be posting more next week.